Picture this. A researcher places a tray of grapes in front of a capuchin monkey, one at a time, watching closely as the animal tracks each addition with obvious attention. One grape, the monkey watches intently. Two grapes, still locked in. Three grapes, tracking perfectly. Then a fourth grape gets added, and something interesting happens. The monkey's precise tracking starts to blur. Ask it to distinguish between 4 grapes and 5 grapes, and suddenly its accuracy drops dramatically, almost as if the animal's brain simply hits an invisible wall. Meanwhile, somewhere in humanity's ancient past, an early human sitting beside a small pile of stones or seeds was doing something a monkey never could. Somehow, at some point, our ancestors broke straight through that same wall and kept counting. So what exactly happened inside the ancient human brain that let us blow past a boundary most primates, including some remarkably intelligent ones, still can't fully cross today? Let's dig into one of the strangest, most underrated stories in the evolution of the human mind. First, let's properly understand this 4-item boundary, because it isn't some cute internet myth or oversimplified science factoid. This limitation is a well-documented cognitive phenomenon called subitizing, and it applies not just to monkeys but to virtually every animal studied for numerical cognition, including humans themselves under certain conditions. Subitizing refers to the ability to instantly recognize small quantities without actually counting them individually. Glance at 2 dots on a page, and you instantly know it's 2 without consciously counting 1, 2. Glance at 3 dots, same thing. 4 dots, still generally instant. But somewhere around 4 or 5, that instant recognition ability collapses, and the brain has to switch strategies entirely, moving from instant recognition toward actual sequential counting. For most animals, including many primates, this subitizing limit represents the absolute ceiling of their numerical ability. They can recognize small quantities instantly up to roughly 3 or 4, but they lack the cognitive tools necessary to push beyond that boundary through deliberate counting. This isn't a matter of animals being unable to perceive that 5 is different from 4. Many species can distinguish larger quantities reasonably well, especially when the difference is substantial, like 6 items versus 12 items. The real limitation lies specifically in precise counting of individual, similar-sized quantities that sit close together on the number line. A monkey might reliably tell you that a pile of 10 bananas is bigger than a pile of 3 bananas, but ask it to precisely track exactly how many items are in a set beyond 4, and that precision falls apart entirely. Now here's where things get fascinating regarding ancient humans, because our ancestors clearly didn't stay trapped behind this same wall. Somewhere across the long evolutionary timeline separating early hominins from modern humans, something changed dramatically enough to allow precise counting well beyond 4, eventually leading toward complex mathematics, calendars, trade systems, and eventually the number-based civilization surrounding us today. Understanding exactly what changed requires digging into brain structure, social complexity, and the practical survival pressures that likely pushed ancient humans toward developing revolutionary cognitive tools. Let's start with brain architecture itself, since this forms the biological foundation underlying everything else we'll discuss. Human brains, compared to those of other primates, developed significantly expanded regions associated with abstract reasoning, particularly within the prefrontal cortex and areas involved in symbolic processing. This expansion didn't happen specifically to create mathematics, since ancient humans obviously weren't consciously evolving toward algebra. Rather, this broader cognitive expansion, driven by pressures related to social complexity, tool use, and environmental problem-solving, happened to create the neural infrastructure that later made numerical abstraction possible as something of a fortunate side effect. This distinction matters enormously because it reveals something important about how numerical cognition actually developed. Ancient humans likely didn't evolve a dedicated counting module the way certain brain regions handle very specific tasks, like facial recognition. Instead, counting ability emerged as a byproduct of more general cognitive flexibility, the same flexibility that allowed early humans to plan multi-step hunting strategies, track complex social relationships across dozens of individuals, and eventually develop symbolic language capable of representing abstract concepts rather than just concrete objects and immediate danger signals. Speaking of language, this connection deserves serious attention, because emerging research increasingly suggests numerical cognition and language development are deeply intertwined in ways scientists are still working to fully understand. Consider something remarkable that anthropologists have observed among certain isolated human cultures still existing today: groups whose languages simply don't contain words for specific numbers beyond very small quantities. Members of these cultures, despite being entirely modern humans with fully capable brains, show significant difficulty performing precise counting tasks beyond roughly 3 or 4 items, essentially hitting that same subitizing wall that limits monkeys, purely because their language never developed the symbolic vocabulary needed to represent larger, precise quantities. This finding is mind-blowing once you sit with it properly. It suggests that raw brain capacity alone wasn't necessarily the deciding factor separating ancient humans from other primates regarding counting ability. Language itself, specifically the development of number words and symbolic counting systems, may have functioned as the actual key that unlocked precise counting beyond 4. Without specific words or symbols representing 5, 6, 7, and beyond, even a modern human brain apparently struggles to maintain the same precision that number-rich languages provide almost effortlessly. So this raises an obvious and important question. Why did ancient humans develop number-specific vocabulary in the first place, while countless other intelligent species never did, despite plenty of species displaying impressive problem-solving ability in other domains? The answer likely traces back toward specific survival pressures unique to ancient human social and economic life. Pressures that simply didn't apply with the same intensity to other species, even remarkably intelligent ones like chimpanzees or elephants. Let's consider resource tracking and distribution, since this represents one of the most practically compelling reasons ancient humans needed precise counting ability that went well beyond simple subitizing. Imagine an ancient community that had just completed a successful large game hunt, resulting in enough meat to feed the entire group for several days. Distributing this resource fairly across a group of, say, 15 or 20 individuals required considerably more precision than simply eyeballing rough quantities. Ancient humans needed methods for tracking exactly how much each family received, ensuring fair distribution that maintained social harmony and prevented the kind of resentment or conflict that unfair distribution could easily trigger within a small, interdependent community where cooperation was absolutely essential for continued survival. This pressure toward precise resource tracking likely intensified considerably as ancient human groups grew larger and more socially complex over time. Small family units of 4 or 5 individuals might reasonably manage resource distribution through rough approximation and direct observation. Larger groups, however, involving multiple families, extended kinship networks, and increasingly complex social obligations, needed something more reliable than simple visual estimation, especially when resources needed dividing across numerous households, each with different numbers of dependents requiring food. Trade and exchange between separate ancient human groups likely reinforced this pressure even further. Unlike most animals, which rarely engage in meaningful resource exchange with unrelated groups of their own species, ancient humans increasingly developed systems of trade involving tools, materials, and food surplus shared between separate bands. Successful trade absolutely requires precise counting ability, since exchanging, say, 7 stone tools for a specific quantity of preserved meat demands both parties agree on exact quantities rather than rough approximation. A trade partner who felt shortchanged due to imprecise counting could easily damage intergroup relationships that ancient communities depended on for genetic diversity, mutual defense, and crisis support during difficult periods. Now let's examine something particularly interesting regarding early counting methods themselves, since ancient humans clearly didn't jump straight from subitizing 4 items directly toward abstract written numerals. Archaeological evidence reveals a fascinating intermediate stage involving tally marks, notched bones, and grouped small objects like pebbles or seeds used specifically as counting aids. The Lobombo bone, an ancient artifact discovered in Africa featuring 29 distinct notches carved into a baboon fibula, represents one of the oldest known examples of deliberate human counting behavior, dating back tens of thousands of years. Similarly, the Ishango bone, discovered in Central Africa, displays notched groupings that many researchers believe represent an early counting or even basic mathematical tally system. These artifacts reveal something important about how ancient humans overcame the same subitizing limitation that still restricts other primates today. Rather than relying purely on mental tracking, which the human brain apparently struggles with beyond roughly 4 items just like other primates. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Ancient humans developed external tools specifically designed to extend their natural cognitive limitations. A notch carved into bone doesn't require holding an increasingly large abstract quantity purely in working memory. It simply requires recognizing one additional mark added to a growing sequence, then physically counting the total number of marks whenever a final tally becomes necessary. This represents a brilliant cognitive workaround, essentially outsourcing memory and precision toward a physical medium rather than relying entirely on unreliable, limited working memory capacity. This tool-assisted counting strategy likely represented one of the most significant cognitive breakthroughs in ancient human history, arguably rivaling the importance of fire mastery or sophisticated tool creation regarding long-term species development. By externalizing numerical tracking onto physical objects, ancient humans essentially created an early form of technology specifically designed to overcome a genuine biological cognitive limitation, allowing precise tracking of quantities that would otherwise remain forever trapped behind that same 4-item wall, still restricting monkeys and countless other species today. Let's also consider finger counting, since this represents perhaps the most universally intuitive early counting method available to ancient humans, one requiring absolutely no specialized tools or materials whatsoever. Human hands conveniently provide 10 readily available counting units, and evidence strongly suggests ancient humans across numerous different regions and time periods independently developed finger-based counting systems. This might explain at least partially why base 10 numerical systems eventually became so widespread across many independently developed ancient civilizations, since the biological convenience of 10 fingers likely provided a natural, intuitive counting framework that required no additional tools or materials to access. Interestingly, this finger counting strategy connects directly back toward our earlier discussion regarding language and symbolic representation. Once ancient humans began consistently using fingers to represent specific quantities, this physical counting method likely reinforced the development of corresponding number words within their spoken language. A community that consistently used a specific finger position to represent, say, the quantity 5 would naturally develop a specific word associated with that exact finger position, gradually building an increasingly sophisticated vocabulary of number words that extended well beyond the natural subitizing limit that other primates remained stuck behind. Now here's a particularly interesting question worth exploring further. If counting tools, finger counting, and number-specific vocabulary all developed as workarounds for a genuine, shared biological limitation, does this mean ancient humans and modern monkeys actually share very similar baseline numerical cognition, differing mainly in cultural and technological development rather than raw brain capacity? Emerging research increasingly suggests this might be the case, which represents a fairly humbling realization once you really sit with it. Human numerical superiority may not stem primarily from vastly superior individual brain capacity compared to other primates. It may stem largely from cultural technology, specifically language and physical counting tools, that ancient humans developed and then passed down across countless generations. Technology that effectively extended natural cognitive limitations that our brains share at a fundamental level with monkeys, apes, and numerous other species. This reframes the entire monkey counting limitation in a fascinating new light. Rather than representing some fundamental gap in raw intelligence separating humans from other primates, the 4-item subitizing wall might represent a shared biological starting point that ancient humans simply found creative, technological ways to push past. while other species never developed the specific cultural tools or evolutionary pressures necessary to do the same. In other words, monkeys aren't necessarily less intelligent regarding numbers in some fundamental biological sense. They simply never developed number words, tally systems, or finger counting cultural traditions the way ancient humans did, largely because their survival pressures and social structures never created the same intense need for precise, large quantity counting that ancient human communities increasingly faced. Let's dig deeper into exactly why ancient human social structure specifically created such intense pressure toward precise counting, since this comparison against typical animal social structure reveals something important. Most animal social groups, even relatively complex ones like wolf packs or primate troops, generally involve smaller group sizes and less economically complex resource management compared to ancient human communities. A wolf pack doesn't need precise counting to successfully coordinate a hunt or divide a kill, since pack sizes remain small enough for direct, individual recognition and rough approximation to work reasonably well without requiring exact numerical precision. Ancient human communities, however, particularly as group sizes expanded and social structures grew increasingly complex involving extended kinship networks, intergroup trade relationships, and sophisticated resource management across changing seasons, faced unique pressure toward precise counting that most other species simply never encountered with comparable intensity. This pressure likely intensified further as ancient humans began developing early forms of resource storage and seasonal planning. Since successfully managing food reserves across an entire winter season required considerably more numerical precision than simply eating whatever happened to be immediately available on any given day. Consider something specific worth appreciating here regarding seasonal planning and resource management. An ancient community storing dried meat, preserved plant material, or other resources intended to last through several challenging winter months needed precise counting ability to successfully manage this kind of long-term resource allocation. Miscounting available food reserves could mean the difference between successfully surviving until spring or running dangerously short of supplies during the harshest, most resource-scarce portion of the year. This kind of high-stakes resource management, requiring precise numerical tracking across extended time periods, created exactly the kind of sustained evolutionary and cultural pressure that likely drove ancient humans toward developing increasingly sophisticated counting systems. Pressure that simply didn't exist with comparable intensity for most other species facing considerably shorter-term survival concerns. Let's also touch on something worth appreciating regarding astronomical observation and early calendar development, since this represents another significant pressure point that likely pushed ancient human counting ability considerably further beyond the basic 4-item subitizing limit. Tracking lunar cycles, seasonal changes, and celestial patterns required counting well beyond small quantities, sometimes involving tracking dozens or even hundreds of days across an extended observational period. Evidence suggests ancient humans developed increasingly sophisticated methods for tracking these longer numerical sequences, likely using notched bones or grouped tally marks similar to those discussed earlier, specifically to monitor astronomical patterns that held genuine practical importance for predicting seasonal changes, migration patterns of prey animals, and optimal timing for various survival activities throughout the year. This astronomical counting pressure created yet another compelling reason for ancient humans to push their numerical cognition well beyond what basic subitizing alone could ever provide. Successfully predicting seasonal transitions or lunar cycles required tracking numbers considerably larger than 4, sometimes extending into the 20s or 30s when tracking a complete lunar cycle, for example. This kind of extended counting requirement almost certainly reinforced and accelerated the development of increasingly sophisticated counting tools and number vocabulary, since the practical benefits of accurate astronomical tracking provided genuine survival advantages worth the cognitive investment required to develop these more complex numerical systems. Now let's circle back toward monkeys specifically, since it's worth appreciating exactly why their evolutionary path never created comparable pressure toward developing similar counting workarounds. Most primate species, despite displaying impressive intelligence across numerous other cognitive domains, simply never faced survival pressures requiring precise counting beyond small quantities. Their social structures, while certainly complex in various ways, generally didn't require the kind of large-scale resource distribution, extended trade relationships, or long-term seasonal planning that increasingly characterized ancient human communities. Without this specific evolutionary pressure, there was simply no strong selective advantage pushing monkey populations toward developing number-specific vocabulary or physical counting tools, meaning their numerical cognition remained anchored at that same basic subitizing limit that likely represents the shared biological starting point across countless different species, including, at some point in our own evolutionary past, ancient humans themselves. This actually connects towards something worth appreciating regarding human uniqueness more broadly. Rather than representing some single, dramatic cognitive leap separating humans from all other species, numerical ability beyond 4 appears to represent a cumulative cultural achievement built gradually across countless generations, layer by layer, tool by tool, word by word. Ancient humans didn't wake up one morning with dramatically superior counting brains compared to their primate cousins. They gradually developed cultural and technological solutions, driven by genuine survival pressure, that slowly pushed their numerical capability further and further beyond that shared biological starting point, eventually creating the sophisticated mathematical systems that modern humans now largely take for granted. Let's consider something worth appreciating regarding how this entire counting development connects toward broader ancient human cognitive evolution generally. The same drive toward abstract symbolic representation that allowed ancient humans to develop number words also likely contributed toward broader language development, artistic expression, and eventually written communication systems. Numbers, in this sense, represent just one specific application of a much broader cognitive capacity for abstract symbolic thinking that increasingly separated ancient humans from other species across numerous different domains simultaneously, not just numerical cognition specifically. It's worth pausing here to appreciate just how remarkable this entire development actually was, especially considering it happened gradually, without any conscious awareness among ancient humans that they were essentially inventing mathematics from scratch through countless small, practical innovations. Nobody sat down one day and deliberately decided to invent counting beyond 4. Instead, countless small pressures, resource distribution challenges, trade negotiations, seasonal planning needs, and astronomical curiosity gradually pushed ancient human communities toward developing increasingly sophisticated numerical tools and vocabulary across enormous spans of time, eventually producing the foundation for everything from basic arithmetic to the advanced mathematics powering modern technology today. So what does this ultimately reveal about why monkeys remain stuck counting only up to roughly 4 while ancient humans managed to push dramatically beyond this same biological starting point? It reveals that raw brain capacity alone likely wasn't the deciding factor separating these outcomes. Instead, specific survival pressures unique to increasingly complex ancient human social and economic life created genuine evolutionary and cultural incentive toward developing number-specific vocabulary and physical counting tools. Technology that effectively extended a shared cognitive limitation that ancient humans, quite recently in evolutionary terms, also once faced themselves. Monkeys never developed comparable pressure requiring precise counting beyond small quantities, meaning their numerical cognition remained anchored at that same basic subitizing boundary that represents, in a humbling sense, the shared starting point connecting humans and countless other species across the animal kingdom. Next time you're effortlessly counting out exact change, checking a calendar date, or calculating a tip at a restaurant without a second thought, take a moment to appreciate just how remarkable this seemingly mundane cognitive ability actually is from an evolutionary perspective. You're relying on a cultural and technological achievement that took countless ancient human generations to develop, built gradually through notched bones, finger counting, spoken number words, and sheer practical necessity, all working together to push human cognition well beyond a biological starting point that still restricts even remarkably intelligent primates like capuchin monkeys today.